The following program is brought to you by Caltech.
Now we'll hear from another one of the next generation of astronomers who've been using the Keck Observatory. Evan Kirby was a Hubble Fellow here at Caltech, working with Judy Cohen up until about last August, and since then he's stayed in the Keck family. He's moved to UC Irvine, and he's going to tell us about archaeology with a telescope.
Thanks, Tom. So Gwen was telling you about galaxies that were billions of light years away. In the next talk, you're going to be hearing about planets that are tens to hundreds of light years away. So we're kind of falling back towards the Milky Way now. I'm going to tell you about something intermediate between those galaxies that are billions of light years away and planets that are tens of light years away. And I'm going to be telling you about dwarf galaxies in the local group. And the reason I like these dwarf galaxies is because they're nearby. The most numerous type of galaxy in the universe are the small galaxies, not the ones like our Milky Way, but a lot smaller than that. And when we can get to these more numerous types of galaxies, it means they're everywhere, including the vicinity just around our own galaxy, the Milky Way. And the reason I like these galaxies that are nearby is because we can see the galaxies for what they are, which is a collection of stars, individual stars. I can point to each star in a galaxy like the Small Magellanic Cloud and observe what that star is made out of. Now, the archaeology part of this talk is because the Keck telescopes are not just astronomical tools, they're archaeological tools. I can dig up what these stars are made of, and the compositions of these stars are going to tell us what these galaxies and these stars were doing at the time that they were born, billions and billions of years ago. Now, the Small Magellanic Cloud is one of the largest dwarf galaxies that lives in the neighborhood around the Milky Way. Something more typical is the Fornax dwarf galaxy. It's a lot uglier, unfortunately, because it doesn't have this gas and all of these dust lanes that make it so contrasty and colorful and beautiful. It's just a ball of old red stars. But I still think it's beautiful. But an even more typical galaxy than Fornax is something that's even smaller. This is the Ursa Minor dwarf galaxy. And you probably are asking yourself now, like, what are you looking at? And the reason is that the dominant thing that your eyes are drawn to in this picture is the foreground veil of stars of the Milky Way. Almost every star that you see, all these bright things that you see here, are stars that are part of our Milky Way. It's the veil that we have to look through and beyond to see the Ursa Minor dwarf galaxy. So if you're in the front row or you have really good eyes, you can probably see there's a concentration of really dim stars in this region. That's the Ursa Minor dwarf galaxy. It's these really puny things that is going to be the subject of this talk. And so I'm going to look at the individual stars with the Keck telescopes and tell you what they're made of, and that way dig up what these stars were doing when they were formed. So to give you a sense of scale for these dwarf galaxies, I'm going to set up some sort of exchange rate between stars and people. And so if the Milky Way has 50 billion stars, which it does, and New York City has 8.2 million people, I'm going to equate those so you can get an idea of what the exchange rate between stars and people is. So the next dwarf galaxy I told you about was Fornax. It's one of the larger dwarf galaxies. And it has 19 million stars, and so it's roughly equivalent to a town with 2,800 people. So if you've ever been to rural Pennsylvania, you might have heard of a place called Strasburg, Pennsylvania, and these two things are equivalent. Now the Ursa Minor dwarf galaxy, which remember is even more typical of one of these dwarf galaxies, has only 560,000 stars, and so it's really in the rural middle of nowhere. So a good analogy would be Loma, Montana. How many people have heard of Loma, Montana? Exactly. So Ursa Minor is just sitting out there in the middle of nowhere. It's just this kind of rural thing. But I can still dig up what those stars are made of because really this Ursa Minor galaxy isn't much farther away than the Fornax galaxy. It still has stars in it, so I can still measure each of its individual stars and tell you what it's made up of. So these dwarf galaxies are interesting because they're basically factories. At least they were a long time ago. And these factories are stars. And when a star, or a certain class of star, nears the end of its life, it blows up quite violently. And when it blows up, it spews a bunch of what we astronomers call metals into the surrounding galaxy. And by metals, I mean any element on the periodic table heavier than helium. Every element on the periodic table heavier than helium was forged inside of a star. Everything that you're made of, other than the hydrogen in the water molecules in your body, was made inside of these stars. Perhaps not the stars in these dwarf galaxies, but stars very similar to the stars in these dwarf galaxies. So this simulation, this is not a real observation of a dwarf galaxy. This is a simulation of a dwarf galaxy, what it would look like at the time that its stars were blowing up. And so early on in this movie, it'll play again so you can see it again, what you saw was this bubble coming out of near the center of the galaxy. That was a supernova blowing up. Now the cool thing about the simulation is that the person who made it, Mr. John Wise, made the simulation such that the colors in this video are as you would actually see them if we could observe this galaxy with a telescope. So this isn't sort of a false color image. It's how the galaxy would actually look through a telescope. So all this red is a bunch of hydrogen. That's all the galaxy starts off with. Now what you can't see are the stars. All you can see is the gas in this galaxy. But one of the stars just blew up there. Now you see sort of green, which represents sulfur. That's actually how sulfur appears. And now you can see some blue, which is how oxygen appears. So you can see as stars blow up, they spew all of these metals, sulfur, oxygen, calcium, titanium, all of these things in the periodic table into the surrounding galaxy. So that's what these galaxies once were, factories. These dwarf galaxies were once small factories. And the units of the factory were these supernovae that were blowing up and making these metals. But that happened a long time ago. All that's left in these galaxies now are just the old stars, these old low-mass stars that live for a very long time, and they don't do much anymore. So these factories are now dead. The machines have been packed up and shipped out. The workers have all been laid off. The foremen are now drowning themselves in drink in some bar somewhere. So that's what they are, just old factories. So you might have known like a different type of old factory. Hopefully you don't get served metals at this particular factory, though, because the products of the dwarf galaxy factories are metals. Remember that. And so the subject of this galactic archaeology are galaxies. It's not villages, but the similarity is quite deep. So this is an ancient village in Israel where a real archaeologist, not me, not an astronomer like me, would go and he would dig up, or he or she would dig up artifacts from this village here. And so, for example, you might dig up a bone or something, a chicken bone. It's like, oh, the people who lived in this village ate chicken. Or maybe a shard of pottery, and this archaeologist noticed that there's some sort of pink tinge on this. What she does is she scrapes off that pink tinge, and she analyzed it in a lab and say, oh, there's some wine of a certain type of grape that comes from a valley over there. So what she's done is figure out the composition of that shard of pottery to figure out what the people in this particular civilization were doing. They were making wine. Okay, so I'm going to be a different type of archaeologist. I'm going to be an astronomical archaeologist. And my subject is going to be galaxies, not villages in Israel, of course. And my tools are not going to be brushes and pickaxes and pliers and things like that, but my tools are going to be the Keck telescopes. This is a beautiful image by Ethan Tweedy late at night. Isn't that gorgeous? I wish there weren't so many clouds. It's kind of bad. It's kind of bad PR for Mauna Kea to have clouds in the image, but they kind of blow away after sunset anyway. So the tools that I'm using are spectrographs, and what these spectrographs are looking at is the light of these stars. So what you're looking at here is a spectrum from the Keck high-res spectrograph of an extremely bright star. In fact, I think this is a spectrum of the sun. And what the spectrograph does is it breaks up the light into a bunch of different colors. What we're looking at is a picture of this star in a bunch of different colors. So there's a picture of the star in this color, and this color, and this color, and this color. So you see a picture of the star in red, yellow, orange, green, blue. But it's not just red, yellow, orange, green, blue. We have not a 8-color box of crayons. We have a 100,000 color box of crayons. So we're coloring in the light of this star with 100,000 different colors. And you notice that we use a lot of the colors quite a lot. We have very great liberalism with sort of these red hues here. But notice that we didn't use these colors. We just chose not to use these colors to color in the star. And that's because the certain chemical composition of the star removes those colors from the light of the star before that light is beamed out towards the Keck telescopes. So there's certain elements inside of these stars that eat the crayons, certain colors of crayons. They really love to eat very specific colors. So for example, there's 3 lines here in the green. And those are lines corresponding to magnesium. So if you have enough magnesium in the star, the magnesium is going to eat those colors, and those colors are not going to be present in the spectrum of that star when that light is beamed towards the Keck telescopes. So by measuring the deficit of these 3 green colors, I can tell you how much magnesium is in this star. It's not just magnesium. I can also tell you a bunch of different elements: silicon, barium, elements you've never heard of, like praseodymium. And so to give you an example of how I can use the amount of those elements to interpret what these galaxies were doing, this is the archaeology part, I'm going to show you what happens to the composition of this galaxy as different events happen in its lifetime. So early on in the galaxy's lifetime, we have just a few stars. So a very small amount of stars are being born at the early part of this galaxy's lifetime. Now, the high-mass stars are going to live for a very short amount of time. The stars that are the most mass in this galaxy don't live very long, and they blow up in a certain kind of event called a Type II supernova. So, pow! That Type II supernova blows up, and when a Type II supernova blows up, it makes a lot of magnesium, which is the chemical symbol Mg, and a little bit of iron, which is the chemical symbol Fe. So the magnesium to iron ratio is quite high, because there's a lot of magnesium and just a little bit of iron. Now, the next generation of stars to form in this galaxy can incorporate that material, can incorporate that magnesium, incorporate that iron. So the next generation of stars to form is going to have a little bit more iron. But again, only the high-mass stars blow up early on in this galaxy, because they're the ones that live for the shortest amount of times. And those high-mass stars are going to continue to produce gas with a high level of magnesium to iron ratio. And so all the first generations of stars to form in this galaxy are going to have high magnesium to iron ratios. But after a certain amount of time, the low-mass stars, which live for a long time, they're going to start to blow up. And when they blow up, it's quite huge. It's what's called a thermonuclear detonation. And this thermonuclear detonation is a big F-bomb in this galaxy. Sorry, actually, it's an Fe bomb. Fe is the chemical symbol for iron, remember? And so these things are just big iron bombs in the galaxy. And when they blow up, they just release a bunch of iron into the galaxy, and the stars that form subsequently after the onset of these Type Ia supernova are going to depress the magnesium to iron ratio, because they don't produce any magnesium, but they produce a ton of iron. So the magnesium to iron ratio is going to drop, because we're adding no more magnesium, but we're adding tons of iron. So this ratio is going to decrease. At the same time, what I'm plotting on the x-axis here is just iron, and that's going to really be increased. So the subsequent generations of stars are going to incorporate more and more iron, but less and less magnesium. So the magnesium to iron ratio drops as the iron increases. Now, this is a pretty average type of star formation history for the galaxy. What I mean by star formation history is how many stars were forming at any given time in the galaxy. Now, if the galaxy were really, really good at its job, and it really liked to form stars very rapidly and efficiently, then a bunch of these high-mass Type II supernova would blow up before the first Type Ia supernova ever had a chance to blow up. So what we would see is sort of a flat line at high magnesium to iron ratio in the galaxy. If, on the other hand, this galaxy was terrible at its job, then it wouldn't blow up very many Type II supernova at all before the first Type Ia supernova turned on. And what we'd see is just a decline of the magnesium to iron ratio as a function of increasing iron. So what we're looking for here is, what is the slope of this ratio? What we're looking for is the presence of these Type Ia supernova, which are the indicators that you have a pretty lazy, inefficient workforce. So let's give you the first example of the galaxy. Now, this is data obtained with the DEIMO spectrograph, not the high-res spectrograph, but the DEIMO spectrograph sitting behind the Keck 2 telescope. In my opinion, it's the best spectrograph behind one of the two best telescopes in the world. What you're looking at here is points, and each point represents an individual star in the dwarf galaxy called Draco. It's called Draco because it lives in the constellation Draco. So here, remember, again, there's the magnesium to iron ratio, but I'm also showing you some different elements, silicon, calcium, titanium, and the average of all four of those elements versus iron. And they roughly follow the same pattern as magnesium to iron. So the story I told you about in the previous slide also applies to silicon, calcium, and titanium. Now, in Draco, what you see is just an inexorable decline of the magnesium to iron and silicon iron and all these other alpha to iron ratios as a function of increasing iron abundance. That indicates that Draco is terrible at its job. If you were the foreman of this factory, you would be fired immediately because your workers are lazy. They're just indolent little things that keep blowing up Type Ia supernova and not a lot of Type II supernova, which indicate that the galaxy is forming stars efficiently. There's none of that. Instead, the galaxy is forming stars very inefficiently. Let's look at a next example. Now, this galaxy is Sculptor. It lives in this constellation Sculptor, hence it has the very uncreative name Sculptor. And what you see here is also a decline in the magnesium to iron ratio, but if you're very observant, you notice that the galaxy reaches a higher level of the iron abundance before it stops forming stars. So this decline in the magnesium to iron ratio and all these other element to iron ratios persists to a higher metallicity. So Sculptor was also pretty bad at its job, but not quite as bad as Draco. And that makes sense because, in the end, Sculptor formed a lot more stars than Draco. It formed a factor of several times more stars than the Draco galaxy did. So it not only formed stars more efficiently, but it formed more stars, period. Now, finally, we move to a galaxy you've already heard about, Fornax, Also, you can guess why it's called Fornax. It lives in the constellation Fornax. But notice now you don't really see that clear pattern for that drop-off of the magnesium to iron ratio anymore, instead of just kind of a mess. And so what this indicates is that this galaxy had a very erratic production schedule. So the magnesium to iron ratio is bouncing up and down all over the place. So what this could indicate, actually I can't really tell you the definitive interpretation, so I'm going to present to you 3 different interpretations for why we see this just big mess in this diagram. So one of them is that Fornax maybe had a burst of star formation, which increased the magnesium to iron ratio, and then the workers decided to all take a break. And so then the magnesium to iron ratio declined again. And they said, oh my God, I'm late for work, I gotta go again. So they start forming more stars again, and the magnesium to iron ratio jumps up again. And then they forget what they're doing, and they go off to the bar again, and they start having a drink, and they forget that they're supposed to be forming stars. And they keep doing this again and again, and the magnesium to iron ratio bounces up and down. So that's one possibility. Another possibility is that the Fornax galaxy formed stars pretty efficiently, but then the iron abundance of the galaxy actually reversed. And this can happen if the galaxy is accreting pristine hydrogen gas from outer space, which would dilute the concentration of iron in the galaxy and have the galaxy come back over here where it started to form stars again. And a third, probably more likely explanation is that Fornax is really several galaxies in one. Parts of the galaxy had a really efficient star formation, so the magnesium to iron ratio remains pretty high throughout the lifetime of the galaxy. And other parts of the galaxy had pretty inefficient star formation. And so it was dominated by type 1a supernova, not a lot of those efficient type 2 supernova. And so the Fornax galaxy really might be 3 galaxies in one that have now been all mixed together, so we can't really tell the difference between them. So let me just sum up here and just conclude that galaxies, what they're doing is they're factories. They're factories that manufacture chemical elements, metals, elements of the periodic table that are heavier than helium. And the Keck telescopes are really archaeological tools, not just astronomical tools, that can dig up what these stars are made of through the tools of spectroscopy. In fact, most of the instruments behind the Keck 1 and 2 telescopes are spectrographs, and one of the purposes of these spectrographs is to figure out what stars and galaxies are made of. And the stellar chemical compositions reveal what the past star formation histories of the galaxies were doing. How many stars are being formed per unit time 14 billion years ago, 12 billion years ago, 10 billion years ago. And finally, most dwarf galaxies were just utterly terrible at doing their jobs. They have one job to do: take gas and turn it into stars. But most of them, as we can tell through those magnesium to iron versus iron diagrams, were really bad at their jobs. But hopefully, we users of the Keck telescopes are not bad at our jobs, and we can continue to do amazing work with these spectrographs. Thank you.